Section 7. Acids, Bases, and Indicators. Colorful Chemistry. Chem Talk. Acids and Bases. Arrhenius' definition of acids and bases. Acids and bases were first classified according to their characteristic properties. As you've experienced, acids and bases have different distinct interactions with indicators, substances that change color with changes in the acidic or basic nature of another material. Some acids react with metals while bases do not. Bases have a characteristic bitter taste and slippery feel, while acids have a characteristic sour taste. In fact, the term acid comes from the Latin word acidus, which means sour. Acids and bases are also good conductors of electricity. In the 19th century, a chemist named Svante Arrhenius attributed the characteristic properties of acids to their ability to produce hydrogen ions when dissolved in water. If you look at the formulas for many common acids, you'll notice that they all have hydrogen as a common element. When these acids are added to a water, a hydrogen atom can be drawn off into the water solution. The hydrogen atom leaves an electron behind, forming a positive hydrogen ion and a negative ion. Consider the action of hydrogen chloride in the aqueous solution. Here's your hydrogen chloride. Here's your water. You get a positive hydrogen ion, and you get a negative chlorine ion. The chemical equation shown above is valuable because of its simplicity. However, in reality, the hydrogen ion is simply a proton and readily attaches itself to a water molecule. The result is called a hydronium ion, right here. So you have your hydrogen ion plus water, and the product is the hydronium ion. To be more complete, the chemical equation above could be written as shown below. Your teacher may allow you to use the simpler form of the equation using the hydrogen ion as opposed to the hydronium ion. Arrhenius also addressed bases and their characteristic properties. He defined a base as a substance that produces hydroxide ions when dissolved in water. Let's look at a base using Arrhenius' definition. When solid sodium hydroxide is dissolved in water, both sodium ions and hydroxide ions are produced, as shown in the chemical equation below. Okay, so here we go. When solid sodium hydroxide is dissolved in water, both sodium ions and hydroxide ions are produced. Over time, scientists have extended their definition of acids and bases beyond Arrhenius' definition to be more inclusive. These include the contributions of scientists like Johannes Bronsted of Denmark, Thomas Lowry of England, and Gilbert Lewis of the United States. Neutralizing acids and bases. When acids and bases react together in a solution, the hydrogen ions and hydroxide ions react in a 1-to-1 ratio to produce water. The remaining ions can join to form a salt. The process of an acid and base reacting to form water and a salt is called neutralization. Because the hydrogen ions and hydroxide ions have formed water, the solution is said to be neutral. The process of neutralization is shown in the chemical equations on the next page. The chemical formula for water is actually H2O. In the equations on the next page, the formula is written as HOH, so that you can see where the hydrogen and hydroxide ions end up. Okay, hydrogen ion, hydroxide ion, water. Okay, here we go. Acid, base, and then that produces your water and your salt. If a suitable indicator is added to the reaction system, it will change colors when neutralization occurs. The point at which the indicator changes color is called the endpoint. Consider the reaction of a strong acid and a strong base, as shown in the equation above. These substances are described as strong because they ionize completely in a solution. For every HCl molecule, one hydrogen ion is released. For every sodium hydroxide molecule, one hydroxide ion is released. These two ions then combine in a 1-to-1 ratio to form a neutral water molecule. Titration. Chemists take advantage of the neutralization process to help determine the concentration of solutions of acids or bases. Suppose you wanted to determine the concentration of an acid solution. You would add measured amounts of a base to the acid until the solution became neutral, or a pH of 7. The name of this experimental procedure is titration. The actual titration technique requires you to know the concentration of the base. It also requires an indicator such as phenolphthalein or a pH meter to determine when the solution reaches the pH of 7, which is neutral. The neutralization point or endpoint of a strong acid titrated with a strong base is at a pH of 7, as shown in the graph for hydrochloric acid versus sodium hydroxide. This being acidic, this being basic, and the goal, if you are trying to neutralize, then the goal is to add enough of both where it would add an amount of both where the product would be a pH of 7 would be neutral. A buffer is a solution that resists changes in pH when small amount of acid or base is added. Because of this buffering effect, titration of a solution of a weak acid with a strong base is slightly different than the titration of a strong acid. When a weak acid, such as acetic acid, is titrated, now that's vinegar, remember? That comes from vinegar from the section before. So when a weak acid, such as acetic acid, so that's an acid within vinegar, is titrated with a strong base, like sodium hydroxide, the endpoint or equivalence point is not pH neutral. Also, the endpoint does not occur as suddenly as with a strong acid. As you neutralize some of the weak acid, some of the acid's conjugate base is formed. In the case of acetic acid, the conjugate base is the acetate ion. The acetate ion is a weak base itself, and a buffer solution is created which contains both the weak acid and its conjugate base. The solution now resists a change in pH as more of the strong base is added. The increase in pH is more gradual, and the endpoint will be shifted to the basic side. The equivalence point or endpoint of acetic acid titrated with a strong base is 8.72, not 7. Okay, so you have your acetic acid, which is derived from vinegar. Then you have your base, acetic ion, and water. This equation shows an equilibrium where acetic acid reacts with the strong base to form an acetate ion forward reaction with the arrow pointing. Okay, so here's the forward reaction with the arrow pointing to the right, this one down here, and water. It also shows the reverse reaction occurring at the same time with the arrow pointing to the left. Okay, so this one. In the reverse reaction, the acetate ion reacts with water to form acetic acid and a hydroxide ion. In equilibrium, the forward and reverse reactions occur at the same rate. The titration of a weak base, such as ammonia, with a strong acid will show these characteristics. The pH will decrease more slowly, endpoint will be shifted to a pH less than 7. And it's all measured in volume. So when you're adding these acids and bases together, you're measuring that in milliliters, which is volume. So you're adding different volumes of liquid acids and liquid bases to each other. Buffers are frequently used intentionally in situations where the chemist wants to avoid large changes in pH. Your blood is a natural buffer based upon the carbon dioxide, carbonic acid, bicarbonate system, which maintains the pH at 7.4. In all cases, a good buffer will absorb small quantities of acid or base with little change in pH. Any acid added to the system reacts with the conjugate base to maintain a constant pH. If a strong base is added to the buffer system, it reacts with the weak acid to maintain a constant pH. The pH scale. Okay, so the scale is to the left, increasingly acidic. The center of the scale is neutral, and the right, and as the scale goes further and further to the right, it increases basic. In this investigation, you observed that one way of describing acids and bases is by examining their effects on indicators. Scientists also use the pH scale to express how acidic or basic a solution is. This number scale ranges from 0 to 14. So there's your 0, there's your 7 for neutral, there's your 14 for basic. Looks like the indicator is blue for basic and red for acid. Okay, this number scale ranges from 0 to 14. Acid solutions have a pH of less than 7. Okay, so once you start going less than 7, that would be considered an acid solution. The more acidic a solution is, the lower the pH. Okay. The higher the the more basic a solution, Okay, here's where we are. The more acidic a solution is, the lower the pH. Okay, down here. Base solutions have a pH greater than 7. Okay, so anything's greater than 7 would be your base solutions. The more basic a solution, the higher the pH. Neutral solutions have a pH of 7. Okay, that's that. The pH of a substance can be measured using methods like a pH meter or probe, pH paper, or universal indicator solution. Acid and base indicators are compounds that are sensitive to pH. The color, let me scroll up here so you can see this. The color of the indicator changes as the pH of the solution changes. Most indicators are weak acids or weak bases that typically exhibit two different colors under varying pH conditions. The table above shows some common laboratory indicators and the colors they display under different pH conditions. The pH scale ranges from 0 to 14 and is used to express the concentration of the hydrogen or hydronium ion of a solution at 25 degrees Celsius. Mathematically, it is defined as the negative logarithm of the hydrogen ion concentration in moles per liter. The term pH stands for power of hydrogen ion. It can be written as, the brackets stand for concentration of hydrogen ions in solution. Because pH is a logarithmic scale, the concentration of the hydrogen ion actually increases or decreases tenfold for each unit on the scale. An acid with a pH of 2 has a hydrogen ion in solution, or a concentration of hydrogen ion in solution that is 10 times greater than an acid with a pH of 3 and 100 times the concentration of an acid with a pH 4. A base with a pH of 10 has a concentration of hydrogen ions in solution that is 10 times less than a base with a pH of 9. The pH of water and equilibrium. To understand the pH of water, you must remember that water contains very small amounts of the positive hydrogen ion. And according to the reaction, pure water has a pH of 7. Therefore, the concentration of hydrogen ions is 1 times 10 to the negative 7th power, calculated from the formula. Since the number of hydrogen ions has to be equal to the number of hydroxyl ions, then the hydroxyl ions is equal to 1 times 10 to the negative 7th. Just as the pH can be calculated from hydrogen ions in water, hydroxyl ions can be calculated from, the values for pH and p-hydroxyl have an inverse relationship. As one goes up, the other goes down. This means that their product is a constant, which is called and is equal to the product of and, or 1 times 10 to the negative 14th. And then here's the expression of that. This will always be true in water. As the concentration of, remember those brackets mean concentration of. As the concentration of hydrogen ions goes up, meaning the solution becomes more acidic, the concentration of hydroxyl ions goes down in proportion, becomes less basic. This makes the calculation, quite simple. Taking the inverse log of the equation, the sum will always equal 14, and right there you're seeing that the sum equals 14. For example, if the pH of a solution is 3, and that is 11, then you can do that. So what you're doing is, they're saying that the sum will always equal 14. So if you had the pH of a solution is 3, then you can automatically figure this out by just taking 14 minus 3, which is 11.